So in the first part of 3.2, we started learning some basic rules of differentiation. And here's a couple quick reminders. The big one, of course, in this section is the derivative of these polynomial type terms, x to the n. You take the exponent, multiply it out in front, and then subtract 1 from the exponent. So when we're working with this kind of stuff, often what we're going to have to do is write things as a power of x, so x to some power. What happens when you differentiate a constant? What do you get when you differentiate a constant? 0. That's kind of nice. Derivative of sine was cosine. But what's the derivative of cosine? Negative sine. Kind of annoying there. Derivative of tangent, well, we'll see that one soon enough. That's going to turn out to be secant squared. Derivative of cotangent is going to be minus cosecant squared. We'll have to prove these things later on. I'm just introducing them now. Derivative of the secant itself is the secant times the tangent. And the derivative of the cosecant is minus the cosecant times the cotangent. Now, the reason I'm mentioning this here is I want to point out something. And right now it only applies for us in terms of the cosine. But take a look at these three that involve derivatives that end up being negative. What's in common to all three of these that you're differentiating? Yeah, the c. If it starts with a c, you differentiate it, you're going to end up with a negative. Here, here, and here. So just something to keep in mind as you look at these things moving forward. You are going to have those things memorized, so try and help out as much as possible. But there's a quick review. One other thing. What happens when I differentiate e to the x? Yeah, get the same. So, okay. With that, let's do a couple reminder problems or some more problems with differentiation. We'll start with problem number 14. Now there's a couple different ways that we can denote the derivative here. And that's all we're trying to find is the derivative of this function. I could call this y prime, or I could call it dy by dx. Really just applying this differential operator to y. When I differentiate this, what do I get? What happens here? 2x minus, yeah, the derivative of x is 1, but it'll be 1 times that constant, so 2x minus 3. What's the derivative of 1? 0. Good, 0. Let's try one like number 24. Y equals 3/4 e to the x plus 2 cosine of x. So same thing. This time we want to calculate the derivative just like the last one. What's the derivative going to be for this one? Any takers on that one? All right, 3/4 e to the x, right? Isn't that cool? Nothing here changes. 3/4 e to the x minus 2 sine of x. Good. You kind of ignore the 2 and you just look right at the cosine. Derivative of cosine is minus sine, so the minus times the 2 gives you your minus 2 sine of x. So looking forward towards your exam, one thing you want to do is you want to study these derivatives. Of course, for the exam, you really only need to know these two right now. The rest of them we're going to learn later on. So for right now, just worry about those two, sine and cosine. Now, one thing I told you to expect was finding the equation of a tangent line. So let's practice that with problem number 36. I'm going to give it to you not quite as the book states it, but more like I would give you on an exam. So we've got g of x is minus 2 cosine of x plus 5. On the exam, I'm going to tell you, I want you to find the equation of a tangent line. I'm just going to give you at, say, x equal pi. I'm not going to give you the y coordinate. I hope and trust that you can find the y coordinate to this graph. How would we find y here? The y coordinate of this point. Yeah, just plug in x, right? So g of pi is negative 2 cosine of pi plus 5. What's the cosine of pi? Negative 1. So negative 1 times 2 is positive 2, plus 5 is 7. So I get a 7 here. And that's good. So that gives me my point on my line. But in order to come up with the equation of the tangent line, I need to know the slope. How are you going to find the slope of the tangent line? Good. We need to take the derivative. So let's work on finding the derivative here. Go back up to the function. Derivative of cosine is, all at once, negative sine. Good job. Negative sine times negative 2 is going to give me a positive 2. So g prime of x is going to be 2 sine of x. What's the derivative of the 5 here? 0. So we got a pretty friendly derivative. Now this measures the derivative, this measures the slope of the tangent line anywhere. Where do we want to find the slope of the tangent line though? At pi. So g prime at pi, 2 sine of pi. Amelia, what's the sine of pi? Amelia. 0. So derivative here is 2 times 0 or just 0. And that's the slope of the tangent line. Thank you. So we've got a slope and we've got a point. So let's plug in our point, pi and 7, and our slope, 0, into this equation. That's going to be y minus 7 equals 0 times x minus pi. And hopefully you can convince yourself that simplifies pretty nicely to y equals 7. So, yay. There's your tangent line. Now, if you're thinking to yourself, wait a minute. That was too easy. I know this guy. He's going to be really mean and try and trick us on the test. You could check it. How could we check our work there? How could you check your answer there? Graph it. Let's graph it. So if you need to borrow a graphic calculator, you know the drill. But let's graph it. So input into the y equals key your function and its derivative, and the tangent line. So hit the y equals key. If there's anything there, we'll clear it out. Negative 2 cosine of x, close parenthesis, plus 5, and then y equals 7. Now, as far as your window is concerned, I would suggest that you put the x coordinate in the center of the action here. So let's go from, say, 0 to 2 pi. Type in the number 2, hit the second button, and then the up arrow key, that gives you pi. When I press enter, it's going to change over to a decimal value. No big deal. How am I going to adjust the graph in the y direction? Yeah, zoom 0. Now, the one annoying thing about it is that sometimes it doesn't give you quite the window that you might want and do otherwise, but it'll work for us here. And you see the tangent line, y equals 7, nice horizontal line, just kisses the top right there at x equal pi. So we're in good shape. In fact, if you hit the trace key, you can see you're on pi and y equals 7 for equation y1. If you hit the down arrow, now you're in equation y2, but you're at the exact same point. So pretty confident that we hit it right on the head in terms of the tangent line. Later on, we're actually going to look for points like that. Look for points where the slope of the tangent line is 0. interesting things happen at those kinds of points. But for the immediate future, we're going to spend a little time practicing finding the equation of a tangent line. So, are you looking okay with problem 36 here? Okay, let's take a look at problem number 34. I'll get you a little bit of a head start, and then I want you to find the equation of the tangent line. So on problem 34, f of x is 2 times x minus 4 squared. You're not going to be able to differentiate this as it stands. You don't have what's called the chain rule yet. So in order to differentiate this, we have to manipulate a little bit. What do you think that's going to entail? Yeah, we're going to have to square that out and then distribute the 2. So when you square out x minus 4, what do you get? Good. And then we'll distribute the 2. 4x squared minus 16x. Excuse me, how about 2x squared? 2x squared minus 16x plus 32. We want to find the equation of the tangent line at x equal 2. So one thing we're going to need is the y-coordinate of our point here. You can plug in x equal 2 here, here, or here. But which one of these, first, second, or third, looks easiest to plug in x equal 2? Yeah, I can go with the first one. So 2 minus 4 is negative 2. But when you square that, you get positive 4 times 2 is 8. So f of 2 equals 8. And the rest is up to you. Find the equation of the tangent line from here. Please. Well, there's a couple things I could ask for in a problem like this. I could just say, find the slope of the tangent line, in which case you take the derivative and put in a given point, and that's the slope of the tangent line. Or I could say, find the equation of the tangent line, in which case you're going to have to go a little bit farther. You're going to have to take that slope along with the point that's on the line and put it together to find the equation. So like in the last problem, if I said find the slope of the tangent line, you could stop right here. If I said find the equation of the tangent line, then you'd have to go through all this stuff as well. Yes. Okay. So there will be one question where I'll say find the equation or find the derivative function using the definition of limit, and I will give the limit. So it'll be really obvious as to what I want, because you will see limit as h approaches 0 of f of x plus h minus f of x over h. So I'll ask you to calculate the derivative using this definition. So that'll be one. There'll be one problem like that, and hopefully you only use it at that one problem.
I was looking at your videos, and I noticed that you put delta x. We were doing step by step. You did delta x. I don't do delta x. Is that fine?
No, I'm sorry, you're gonna fail. No, I'm kidding. Yeah. No, delta x is fine. H is fine. Yeah. H, delta x. Yeah, whatever is convenient for you. I like using h because it's a little more friendly. But if you're comfortable with delta x, that works too. Yep. So on the last one, here's your sine function. You expect the tangent line at this point to go through like that. But what if you graphed it and it went through like this? Well, that's not a tangent line, right? It's intersecting the graph. So I was just looking to see that the geometry looked correct. It's not a complete proof. Good. let's look at this one together, and then we'll do another one after this. First thing I need to do is find the slope of the tangent line. What tells me the slope of the tangent line? Yeah, the value of the derivative at a particular point. So what's the derivative? F prime of x. 4x minus 16. The slope of the tangent line is going to be f prime at what point? At 2. So f prime of 2 is going to be 4 times 2 minus 16, which is negative 8. So I got all I need. I've got my slope and my point, which is 2 and 8. So let's plug that in. Y minus y1 equals m times x minus x1. And when we distribute and solve, you get negative 8x plus 16. Moving the 8 over, 16 plus 8 is 24. Now, like the last one, this one should check out. If I was to graph this function and this line, they should just touch at this point, 2 and 8. So let's see that that happens. So 2 times x minus 2, or excuse me, x minus 4 squared, and negative 8x plus 24. I'm going to center my window around the point x equal 2, so this time I'll go, say, between 0 and 4. Let's see what we get when we press zoom 0. So there's one graph, and there's another one. If you have the wrong graph, suppose that you have something like 8x plus 24, or 8x minus 24. Maybe you copied it wrong or something like that. Let's see, 8x, let's do 8x plus 5 or something like that. Your graph is going to be something other than a nice line that just touches your function. It's going to intersect it at some weird angle, or maybe intersect it twice, etc. But you're not going to get the nice behavior that we have for this one. So, is it a complete check? No. But it is a check of your work nonetheless. I took the derivative here. So 2 times 2 is 4. Subtract 1 from the exponent, leaves me with x to the first power. When you differentiate x, the 1 here is going to multiply the 16. So 1 times 16, or negative 16, depending on how you want to look at it. That leaves me with negative 16 times x to the 0 power. But what's x to the 0 power? It's 1. So I'll just leave that as 4x minus 16. So that's how we got the derivative there. Okay, thank you. Anything else on problem 34? Yes, sir. Sure. So the step that I kind of left out was I distributed this and got negative 8x plus 16. Oh, well, there's really a couple steps. The first thing I did was I found this thing right here, which is the derivative. The derivative tells you the slope of the tangent line. So where did we want to find the slope of the tangent line? For what value? Yeah, at x equal 2. Good. So at x equal 2, we wanted to know the slope of the tangent line. So if we put in a 2 into here, it's 4 times 2 is 8, minus 16 is negative 8. So that's the slope of the tangent line. We put that together with the point, 2 and 8, and then we're able to find our equation. So does that help out? Okay, good. Appreciate the question. I want you to try another one, problem 32. If I didn't get to come by you on the last example, make sure I come by on this one. And I do that not to like be, mean or anything like that. I just want to see how people are doing, make sure that you have a good understanding of what we're doing here. So f of x is 2 minus 4 over x. Let me help you out a little bit to start, or maybe you can help yourselves out. Somebody tell me how you rewrite this to get started so that you can find the derivative. Thank you, gentlemen. So you're going to rewrite that so that now you can differentiate this with the rules that you have. Right here, you're going to need something that you'd be really fond of by the end of the semester called the quotient rule. But that's a joy for another day. Right now, let's see if we can't find the equation of the tangent line at x equal 4. So, same game as it was with the last one. Like I said, I'll walk around, try and help out, see how you're doing, etc. tangent line at 4.
This
3.2.
Do we get extra points for that?
Should we talk to someone from? Let's talk to someone from Holly, Michigan. Say hello.
Hi.
Speaker. Yeah, speaker. Hello.
Hi.
All right. You're shy. Okay. So let's get back to things here. The thing we're going to need next is, there's a couple things we can come up with next. Let's find the point here. So f at 4 is going to be 2 minus 4 over 4. 2 minus 1 is 1. So our point at x equals 4 really has coordinates of 4 and 1. So that's our point. But we also need the slope of the tangent line at that point, and the slope comes from the derivative. So as far as the derivative function is concerned, well, let's go back up here. Derivative of a constant, what's that? 0. So f prime of x is going to be 0. When we differentiate this term here, it's going to be the negative 1 times the negative 4, which would be a positive 4. What happens to the exponent? What do you do to the exponent? Subtract 1. Yeah, good. So we get to the negative second power. And a lot of you clean it up as 4 over x squared, and that's great. So that tells you the slope of the tangent line. We need to find the slope of the tangent line at x equals 4. So f prime of 4, John, what did you get for f prime of 4? How'd that simplify?
It's 2 minus 1.
Oh, f prime of 4. It's all right. It's all right. So the slope of the tangent line is 1/4. There's your slope. There's your point. Y minus y1 equals m times x minus x1. So y minus 1 equals 1/4 x minus 4. Interestingly enough, the 1's are going to cancel each other out. When you add 1 to both sides, you end up with a very simple equation for a tangent line. Y equals 1/4 times x. How does that look there for the equation of the tangent line? How many people got that? All right, a little over half. Good. If you didn't get it, did you see what you might have mistaken, or did you catch a mistake, or have a question? Yeah.
After you found the first part of the derivative, 4x to the negative 2 power, then you plug in 4 again.
Well, yeah, the 4 was just part of the derivative. All right. The reason I plugged in x equals 4 is because when I do that, I find the slope of the tangent line at that point. So if you plug in a value of x into the derivative, that gives you the slope of the tangent line at that value of x. So the slope there was 1/4. Anything else bothering you on this one? True?
I got lost where you guys got something at 0. Yeah, it was close.
Down here?
No. It was 0 plus 4x.
Oh, derivative of a constant is 0, right? So let's look back up here then. We're going to differentiate this term. And you know what? Let me start down here. Let's just differentiate x to the negative first power, and I'll leave the negative 4 out in front of this. That is, I'll multiply by that when I'm all done. So it's going to be negative 4. Now what's our rule for differentiating these kinds of terms? You bring the exponent out in front, and then you subtract 1 from the exponent. So what's negative 1 minus 1? Negative 1 minus 1 is negative 2, and negative 4 times negative 1 is positive 4. So negative 1 times negative 4 is positive 4. So does that help? You're still... Yeah, you could rewrite this at that point as 4 over x squared, just putting it in the denominator to make the exponent positive. All right. There was another person that was a little stuck on that. Did that help out as well? Okay. All right. Well, I appreciate the questions. Thank you. We're going to spend a little more time practicing with the derivative calculation itself. And that's going to start first with problem number 44. So problem number 44. H of x is 4x cubed plus 2x plus 5 over x. Now I'd be happy to tell you that you could find the derivative of the numerator and divide it by the derivative of the denominator and be all done. But I can't. Can't do that. It just doesn't work that way. Soon enough, we will learn how to find the derivative of a quotient. And to that end, you'll learn the quotient rule, and you're going to be really, really happy because it's going to be your favorite rule for differentiating. But until we get there, we have to do this. We're going to take and divide each of the terms in the numerator by the term in the denominator. So we're reformulating this into something that we can differentiate. Now, does this simplify it all? Yeah. You can simplify it here. Good. So 4x squared plus 2. And let's rewrite 5 over x. How could I rewrite that as a convenient expression to differentiate? Yes. 5x to the negative first power. So this is still h of x. But writing it like that makes it a lot easier to find h prime. So see if you can't find the derivative. I'll give you a few seconds, and then compare it to your neighbor. Check it out and see how you do compared to them. So kind of a low stress thing. See what you guys get. And we'll check up here. All right. Compare answers. Let me hear some chitter chatter. See how you guys are doing. All right. Sam, did you check it? Did you make a friend? Did you make a friend? Okay, good. Good. All right. So how are we looking here? 2 times 4 is 8. Subtract 1 from the exponent, 8x to the first power. How about the second one? 0. And then for the third one, negative 5x to the negative second power. You can, if you want to, clean it up like this. That's fine. I'm not worried about you using positive exponents so that you have to get rid of the negative exponents. This is fine. I don't want to see the plus 0, but other than that, we're good. Okay, let's try problem number 50 and 52. F of x is 2 over the cube root of x plus 3 cosine of x. 52, g of x is the square root of x minus 3 e to the x. What's one thing we're going to have to do in problem number 50? Yeah, we're going to have to do something with the root. So instead of the cube root of x, I could write that as x to what power? X to the 1/3 power, or somebody suggested negative 1/3. You can get that out of the denominator by making it an x to the negative 1/3. So probably easiest to differentiate it from here. You're going to have to do likewise with problem number 52. But again, I want you to work on these two. See if you can't find the derivatives, f prime and g prime.
it still stays.
Because I think it's part of it. Like, if it was just an X, it would still be part of it. So, yeah, it's just a.
Well, because it would run just like any other output.
Yeah.
Oh, I didn't have to ask. I already did.
Okay.
Two. I was looking for
Four thirds. So you're negative one third minus one is 4 thirds.
This is getting a little small. I just can't read it.
Yeah.
Negative one third dash.
No, I think you're at the right there.
Negative one third minus one.
Oh, yeah, it would be.
Okay, I'll get you guys next time I do a little roundabout.
Oh, yeah, that's what I meant.
Okay, so first things first, 2 times negative 1/3 is going to be negative 2/3. Subtract 1 from here. You know, I saw somebody do it, and there's no shame in it. If you're not sure, it's like, is that negative 2/3 or what? Take out your calculator. It's not a big deal. You know, I'd rather you get it right than not. So if you do negative 1 divided by 3 minus 1, and you get some number, well, do answer the fraction. Oh yeah, negative 4/3. I mean, at the very least, get it right, even if it means you got to take out your calculator for a second. Yes?
For those, do you care necessarily how we write it? Because I put negative 1 1/3. I don't know if that's.
I myself wouldn't write it as negative 1 1/3, but somebody else did, and yeah, I got no issue with that. Just for practice, I'm going to rewrite it using radicals, but before that, there's a question back here as well. You hit the math key and then press enter twice. And that'll convert your decimals to fractions where possible. Now, for instance, if you take a look at the square root of 2, then I do answer the fraction, it's not giving me anything. It's because square root of 2 is not a rational number. You can't write it as a fraction. So there's a cool proof of that sometime. So last but not least, the 3 is in the denominator. I'm going to put this in the denominator, so negative 2 stays up. So x to the 4/3 minus 3 sine of x. X to the 4/3, 3 comes over, 4 drops down, leaves me with 3 times the cube root of x to the 4th minus 3 sine of x. Now I'm only doing this last step just for the practice. I'm really fine with it if you answer here or if you answer down here. Either one works. They're both fine. I will give you a heads up. Later on, you are going to have to work with these a little bit further. So it's not a bad idea to get in the habit of simplifying them now, because later on when you set this equal to 0 or something else and have to solve, it's just nice to have the expressions cleaned up rather than work with it from here. So, yes? No, the one in the middle is fine. I just, you know, I don't know, I guess if you're going here, I'd go here. All right. But yeah, there's nothing wrong with the one in the middle either. Yeah. For problem 52, that's x to the 1/2 minus 3e to the x. Same kind of game. G prime of x. The 1/2 comes out in front. Subtract 1. Gives me a minus 1/2. Derivative of e to the x is just e to the x, so this part doesn't change. If I do what I did in the last one, that'd be 2 over x to the 1/2 power minus 3e to the x, or 1 over 2 square roots of x minus 3e to the x. So again, all three of these are acceptable. I guess I kind of regard this as being a transition step to this, but yeah, any of these is fine. Yes, please. I'd like to see that. You know, there are occasions where I will get a little bit picky, but I don't know. Yeah, it's certainly not g of x. There shouldn't be any confusion about that. Yes, sir. Great question. You subtract 1 from the exponent if you have a polynomial type expression. So like this. But e to the x is not a polynomial. It's a special function. So if it's in this form, then you're going to subtract 1 from the exponent and then multiply by that exponent out in front. But derivative of e to the x is just e to the x. Okay? So don't get fooled in subtracting 1 there. Yes, sir?
I was going to ask you about paper.
Let's try problem number 58. So the goal in 58 is to find, I think it's where you have a horizontal tangent line. So let me flip back open there. So our function is y equals x cubed plus x, and it says determine the points, if any, at which the graph of the function has a horizontal tangent line. So here's our function, 58, y equals x cubed plus x. So where are we going to have a horizontal tangent line? Well, let's understand what it means to have a horizontal tangent line. What's a horizontal tangent line going to look like in terms of its slope? 0. So we need to find where this function has a horizontal tangent line. How are we going to do that? Perfect. Well, the slope of a horizontal line is 0. So if you want to find a horizontal tangent line, you want to find where the slope of the tangent line is 0. And the slope of the tangent line is measured by the derivative. So d by dx of this. So Justin, what's the derivative here, please?
2x plus 5 to the power of 2.
2x to the 2.
3x to the 2. And what's the derivative of x? Good. 3x squared plus 1. And now I want to set that equal to 0 because that's the slope of a horizontal line. Horizontal line. Well, let's solve for x. That's 3x squared equals negative 1. X squared equals negative 1/3. And, uh-oh, running into problems. Yeah, we're not going to work with imaginary numbers. So basically there's no solution. There's no point on the graph of this function where the tangent line is horizontal. We're just not going to work with imaginary solutions. So that's it. You had another question? Go ahead. dy by dx. That's just another name of y prime. They mean the same thing. Well, there's a slight difference there. D by dx means you're going to take the derivative of what follows. So d by dx of, say, 4x squared is 8x. So that means I'm going to take the derivative of this. Here, I've taken the derivative of y. So, yes. So, if that's y, then this is dy by dx. So this is the before, and that's the after. So yeah, it's just some notation. As confusing as it may seem, it's actually been pretty refined. If you look back historically, sometimes they use some notation that would just be really painful to look at today, especially for square roots. Let's start problem number 64. Y equals the square root of 3 times x plus 2 cosine of x. We're going to play the same game. We want to find out where does this have a horizontal tangent. Now it's important to notice and realize that that x is not under the radical. It's the square root of 3 times x. It's not the square root of 3x. So I don't need to rewrite the square root of 3 when I differentiate this. dy by dx. Andrea, what's the derivative of the first part? Well, no. Put it all together. 1 times derivative of x is 1 times the square root of 3. Just square root of 3. Because you differentiate that, you get a 1, and it's going to be the constant times the derivative of that. All right?
The radical 3 change.
Radical 3 is just a constant.
But
So,
the constant turns to 0.
well, we'll see a little bit more about this later on when we do the product rule. But as far as differentiating is concerned, when you have a derivative of a function, derivative d by dx of a constant times a function, one of the rules that we saw the other day was we're going to take that constant out. It's going to be the constant times the derivative of the function. So I'm just going to look past this, differentiate the function, and then multiply by the constant. Derivative of 2 cosine of x minus 2 sine of x. So square root of 3 minus 2 sine of x. What am I going to set that equal to? 0. So 0, and we're going to solve for x. So I'm going to move the 2 sine of x to the other side. 2 sine of x equals square root of 3. Why do you suppose I move the 2 sine of x to the left-hand side like that? Yeah, make it positive. I got rid of the negative that way. It's just a little cleaner, less mistakes. Divide by 2, sine of x equals square root of 3 over 2. X equals the inverse sine of the square root of 3 over 2. Now, some of you might look at that and go, oh, man, I was terrible with these things. It's been forever since I had trig. And I get it. I totally get it. So what I might do for you on the test is put a blank unit circle on the back so you can fill it out if you want. But here's a little workaround for those of you who are just really, really unhappy every time you have to deal with trig. No, it wouldn't. It's not 30 degrees. It's a good question. 60, yeah. So if you look at that and nothing's coming to mind, then here's what you can do. Put your calculator, for the moment, in degrees. Because you're not going to recognize the answer in radians. You're going to look at it and go, oh, I don't know. I would do the same. I wouldn't recognize it in radians. So let's put it, hit the mode key, go to degrees. And once it's in degrees, I'll type the second key and then the sine key. That's the inverse sine. It has nothing whatsoever to do with the cosecant. It is not the reciprocal of the sine. This gives you the angle whose sine is square root of 3 over 2. So hit the second key, square root of 3. Make sure you hit the right arrow to get out of the square root. Divided by 2. And there you go. Oh, 60 degrees. Now, convert that back into radians. 60 degrees is what in terms of radians? Pi over 3. So technically, there's another solution. And I think they ask you for the solutions in 0 to 2 pi. So let's think about that for just a second. Okay, so zoom out a little bit. Sine is your y coordinate on the unit circle. So square root of 3 over 2 gave me a y coordinate up here at 60 degrees. But there's another one. This guy has a twin on the other side of the unit circle over here. What's that other angle? 120. The way you can get that is you realize, oh, well, this angle is 60. 180 minus 60 gives me 120 degrees. So there's your two solutions, pi over 3 and 2 pi over 3. Yeah, if you left your calculator in degrees on that, or in radians on that one, then the answer you would have gotten from the inverse sine would be like this, 1.047, which doesn't look familiar at all. Any thoughts on problem 64? Yeah, go ahead, please.
So you know both the answers pi over 3 or 2 pi over 3?
Yeah, let me take a look back at the book, but I think they ask you for the answers in 0 to 2 pi. Yes. Yeah, so there's two places there. If you look at the graph, you can see what's happening with that. So let me pull up the graph here real quick. Let's shut these down. Here's your graph. Let's try and make that a little bit better. There you go. But you can see that there's 2 points where the function kind of levels off. Right here, you've got a horizontal tangent. And then down here, you have a horizontal tangent. So those are the 2 points we were looking for. Okay? So it's nice to be able to look back at this graphically and see that you got it right. Yes, sir?
When you look at that,
Well, the tangent, at least locally, is going to be just right. Yeah, eventually, if you extend it far enough, it is going to intersect the graph more. But for now, the height here looks like 2 square roots of 2. So we'll do y equals 2 and the square root of 2. And yeah, you're right. Eventually, this tangent line will cut through the graph. But near the point, it's the tangent line that we expect. Anything else on 64? That's a good one. So, get some questions. Yes, please.
it says 0 to 2 pi, so you only gotta find that.
Well, there's only 2 solutions to this, right? Because if you go around here any further, then the y coordinate is negative. So there's not going to be any more solutions to where y equals, and this line is really y equals square root of 3 over 2. There's only 2 solutions, up here and here. So, good question. Yeah? Did you have a follow-up on that one? True?
No, I see it now.
Okay. You can see it from the graph, too. So 2 pi is going to be 6.28. In the interval 0 to 6.28, there's only 2 places that it looks horizontal. I mean, I know I'm off the chart here a little bit with the graph, but that doesn't look like it's going to level out anytime soon. All right. Well done. I appreciate the questions. Is there one more, Trevor? No.
This might not be completely relevant, like with what we've learned now, but how would you, because you said e to the x is a special function, so it wouldn't apply by the normal rules.
Well, it's not that it doesn't apply by the normal rules. It's just it's special in that it's its own derivative.
Yeah.
It measures its own rate of change. So that's pretty unique.
How would you do the derivative of a function where it's something else to the power of x?
Well, we don't know all the rules we need to know yet. So if we had e to the x squared, that's something we need the chain rule for. But that's coming up in a couple sections. Right now, you couldn't differentiate that with what you know.
All right.
All right. So, no, it's a great question. I'm going to have to ask you to hang on to it for a little while longer until we learn the chain rule. So, okay, let's move on to problem number 100 then. Oh. Yes, please.
Problem
62.
62.
Sure. let's take a quick look at 62. So same game in 62. We've got y equals, what was it, x plus 4e to the x? X plus 4e to the x. Again, we're trying to find a place where the tangent line is horizontal. Tell you what, let's do this first. Before we actually go through the calculations, let's see if we can't predict if we're going to find a solution here. So let me graph this. Y equals x plus 4, excuse me, did I get that right?
X plus 4.
Yeah, x plus 4e to the x. Yeah. X plus 4e to the x. And let's turn that on. And kind of zoom out a little bit. Does there look like there's going to be a solution here? Does it look like there's a place where there's going to be a horizontal tangent? No, nothing I see, but could be wrong.
Didn't you say e to the x is like special? Like that's gonna become e to the x minus 1.
No, the derivative of e to the x is going to be e to the x.
Oh, it's just e to the x.
Yes.
Okay.
So let's look back here at the function. Oops, wrong one. There we go. dy by dx. Natasha, what's dy by dx going to be, please? All right, John.
1 plus 4, 1 plus 4, x.
Good. 1 plus 4 e to the x. We want to know where this is equal to 0. So we solve, we get 4 e to the x equals negative 1. E to the x equals minus 1/4. And there is no solution here. That's a great question. I'll give you two different answers. The first of all, if we were to solve here, if I had e to the x equals some number, what would I have to do to get x out of the exponent? Do the natural log. All right, so ln here, ln here. Somebody do me a favor and calculate the natural log of negative 0.25. What happens? Go ahead. It's undefined. All right, so unless your calculator has your mode set to complex, then it's undefined. Undefined. So there's no solution. Negative numbers are outside of the domain of the log function. So, bummer.
If it was a different number.
It has to be a positive number is really the bottom. Yeah, then you'd get a solution.
How do you go from there?
Well, let's see. If this was like a minus here, then there would be a point where there's a solution, right? Point up here. Probably at negative 1/4 or something. Well, maybe not negative 1/4. But there would be a solution if there was a minus there. But there isn't. Our problem gave us a positive number. The reason, another kind of graphical reason that you're not getting a solution, if you look at y equals e to the x on a graph, that graph always lies above the x-axis. You'll never have e to the x equaling something negative. It just doesn't happen. So we saw that when we tried to calculate the solution here algebraically.
To be honest with you, I did 61 and I got to the point and I got stuck.
All right, well, you're going to have to come see me or come see me about that one. I do want to get to problem number 100, so if it's all right, let's move on to problem number 100. Problem number 100 gives you s of t equals negative 16 t squared plus v naught t plus h naught. Let me describe what all this stuff is. This is what's called the position function. So s of t is the position function. It tells you how high an object is above the ground under certain conditions. So, describes the height above the ground of a function. Under what conditions? Well, I'm glad you asked. V naught. That's the initial velocity with which your object is hurled upwards. So, initial velocity. H naught is the initial height. You do not have to memorize this function, nor the notation and stuff like that. If I wanted you to do a problem like this, I would give it to you and describe that to you. You do have to know how to use it. Yes, sir?
In the book where you put H naught, it has S naught. Is that just going to be the same? It's just different.
Yeah, it's just a different name for it. Yeah, I like H naught because H naught to me sounds like initial height. Height that times 0. Now, a couple things about this function. If you change your position, you're moving. And if you change your position, then you have a velocity. So, what function do we know that represents the way another function changes? The rate of change of a function is measured by the derivative. So v of t is the velocity function. Velocity function. That measures the rate of change of the position. How fast are you falling? What happens if you change your rate of speed? What are you doing when you change your rate of speed? You're accelerating. So a of t is going to be v prime of t. That's your acceleration function. Now typically we stop there, and that's where we're going to stop in this course, is with the second derivative. If you notice or think about it, another name for a of t would be s double prime of t. So it's the second derivative of your position function. You can actually go one farther. If you look at the rate of change of your acceleration, when you change your acceleration, you're jerking. So if you want to insult somebody in a really highbrow way, you can call them a third derivative, because really you're calling them a jerk. The jerk function, j of t, is s triple prime of t. So just make sure the person you're insulting doesn't know calculus. All right, let's put aside the jerk function a little bit and actually get down to business with problem number 100. In problem number 100, they tell you that the initial velocity of an object is negative 22 feet per second, and that its initial height was 220 feet. So let's put that into our function and see what we get for s of t. S of t would then be negative 16t squared minus 22t plus 220. So there's your position function. So you're throwing an object downwards. It's not enough that you're 220 feet above the ground and gravity is going to do a pretty good job of accelerating it. You're also throwing it downwards with an initial speed of 22 feet per second. So you're not actually giving a lot of velocity, but a little bit. Let's take a look at the questions that they ask you here in problem number 100. It says, what is its velocity after 3 seconds? Justin? None. None of this. You do not have to memorize anything. So when I ask you a question on the test about this, I will give you this function and I will describe all of it. Okay. What you need to know is, how to calculate the derivative. So the derivative here v prime of t. Good. Minus 32t minus 22. Exactly. If you want to know the velocity after 3 seconds, then plug in a t equal 3. So v of 3 would be negative 32 times 3 minus 22. That's what, negative 118? What units go here? Feet per second or feet per second squared? Feet per second. Feet per second squared would be an acceleration. So feet per second would be the correct units there for velocity. It can't just be feet, because that's a distance. It can't just be seconds, because that's a time. Feet per second. Distance per unit time would be a correct unit for a velocity. Two times negative 16. That help? What this reflects here is that gravity is accelerating things downwards. It's always going to be tugging towards the center of the Earth.
Which things were given and which things did you calculate?
Okay. This formula was given. And these two initial values were given. So when I plugged this and this into here, then I got the equation that I'm going to underline in a very manly pink. All right, so all I did was I plugged that information into here, and I got my position function. The derivative of the position function is then something that I hope you can calculate. Differentiate s of t, get v of t. We plugged in 3 to finish it up. V is velocity. V of t is the derivative of s of t, yes. Just substituting in a particular value, they ask for the velocity after 3 seconds. So how fast is your object traveling after 3 seconds? Let's finish it up with problem number 100. It says, what is the velocity after falling 108 feet? Well, you can't just plug in 108, because that would be the velocity after 108 seconds. I'm thinking that after 108 seconds, this would have hit the ground a long time ago by then. So we'll have to do some more thinking then. What's the velocity after 108 seconds? Or not, or after 108 feet, I should say. Yes, sir.
For h sub 0, couldn't you put in 108?
Close. We do have to look back at the original position function. You're still close. We do have to look back at the original position function right here. Let's see, what do we need to know in order to solve this? We need to know the time, right? So basically we need to know at what time is the position 108. Can anyone figure out how I'm going to solve for that? Not quite.
Oh, you isolate t? Like move everything?
Closer. I'm going to set the position function equal to 108. And then solve. This is just a quadratic equation. So one of the things that I assume you can do is solve quadratic equations. I'll subtract 108 from both sides. I get negative 16t squared minus 22t plus 112 equals 0. Volunteer to factor that one for me? No takers? All right. Liam, I'm stuck solving a quadratic equation that I just really don't want to solve. And I don't know how it factors, if it factors at all. What could I do? Well, even if this does factor, I don't think I want to try. Yeah, the quadratic formula. Good. So The quadratic formula is something that I assume that you know. So in case you don't, here it is here. I promise not to sing this along to my favorite college fight song. Now, if you have trouble using the quadratic formula, come see me. Come see Mimi. I'll get you some help. But you could make your life a little bit easier if you wanted to divide everything here through by -2. Might be a little bit friendlier because you'll get rid of some of these negative values. Or not. It's up to you. You want to just run it through like this, or do you want to divide through by -2? All right, run it through like that. Good choice. So A, B, and C would be -16, -22, and 112. Personally, I think we should have divided by -2. Having a negative value for A is kind of a pain. Negative of -22 plus or minus the square root of -22 squared minus 4 times -16 times positive 112 all over 2 times -16. And you're actually going to have to look at both solutions. I'm not going to take the time here, but you do end up with a solution of about 2.04611 for one of these values. Okay, so, whew. Yes? We solved the quadratic equation using the quadratic formula. Because I subtracted 108 from both sides. Okay. I'm not done though. What's the last thing I need to do to finish this one off? I wanted the velocity at this time. So I figured out how long it's going to take to drop 108 feet, but I haven't figured out the velocity yet. So what's the velocity then? How do I find the velocity? You plug it in the velocity function, right? V of 2.046, etc. is going to be about -87, I don't know, 0.475. And that's going to be feet per second. So I'm pretty sure that's a little bit less than 60 miles an hour would be the speed on that. Yeah, you plug that into this one up here. Right here, and I'll underline that one in blue. For homework, try 1 through 65, 99, and 101, and 103. Good question. No, I didn't forget to say EOO. Yeah, sorry about that. Theoretically, though, some of these were done last weekend, right? So hopefully you've got like less than half of that to do anyways. So, in theory.